we have talked about the limit as x approaches a of f of x, and if this is equal to some L, we said that the limiting value of this function f of L is L as x approaches a, which means that as we keep picking value of x that are so close to a, what is the value that we can round off to, or what is the nearest output of this function here that we're actually getting when you're picking a value on the left and also on the right of this. And this L was called the limiting of this particular function. Whereas whenever we're choosing our value a, our value was a finite value. And then we also moved to saying that the limit as x approaches a, where a is a finite value, of f of x is equal to infinity. If, let's say, as we keep approaching a, we are actually having a vertical asymptote at x is equal to a. So we talked about vertical asymptote at x is equal to a. So we can either have the limit as x approaches that to be positive infinity, or it can be negative infinity, or it cannot exist. Maybe on the left we have positive infinity, on the right we have negative infinity, or vice versa. So we talked about this, and we talked about this particular thing here. And we said regarding this particular limit, this simply means that if this function is not defined at a, we said that, okay, when I'm taking a and I'm plugging inside here, I'm not getting this L. We said that here we can either end up having a removable discontinuity at x is equal to a, or we can actually find out that if I'm plugging in here and I end up getting the same L, we said that actually this function is continuous at that point a. So those are some of the things that we talked about when it comes to the limit. And studying limits, I have to be honest about this. Once you can understand what we are actually doing with these limits, you have already passed the course. Because these limits, I think, are the only thing that if let's say you understand the limits and you are good with limits and continuity, then I can tell you that you are actually about to get a distinction in this course, because those are the only things that are a little bit challenging, and also you can add those are the only things that are a little bit challenging. Everything else is going to be easy, and once you understand these limits, and then everything that we are about to do will be very, 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 very easy so far. So just try and revise and make sure that you understand the limits, and both this one, most of the time, if you noticed, this one was when we're actually having a number over 0, and 0 over 0 fell, it started to fall on this particular side. And why did we study these limits? It's because we want to fully characterize a function so that we know that if I have my a there and I am actually having a 0 over 0, I know that I'm actually having a removable discontinuity there, or I have a hole. It can happen that maybe this function is defined there, or it's defined down there, or it's not defined, it's just an empty hole throughout. And then we also talked about when we have an a and we have a vertical asymptote at that point, that the function can either be going all the way like this and then going like this, or it can be going like this and like this around that particular asymptote. And once we understand our holes, that at that point there is a hole, at that point there is a vertical asymptote, and we understand the y-intercept, we understand the x-intercepts, then we are so close to fully characterize our function, because now the next thing that will actually be missing is when is this function gonna be increasing, When is this function going to be decreasing? When is this function is actually going to be having a turning point? And when this function is actually going to have saddle points? And when is this function is actually going to be actually concave up or concave down? And what is happening if we keep increasing our function? If we keep increasing our x, what will be the behavior of the function? So those are the things that we are actually getting closer to. That is why now we want to find out what is the meaning of the limit as x approaches positive infinity, or simply infinity, of f of x. What do we mean by this? And also, what do we mean by saying the limit as x approaches negative infinity of f of x is equal to some m? And also, how do we end up evaluating these particular limits? And what will be the meaning of the limit as x approaches infinity of f of x if we say that this one is equal to maybe negative infinity or positive infinity? And also, what will be the meaning of saying x as x approaches negative infinity of f of x is equal to maybe plus infinity or negative infinity? What will be the meaning of these four scenarios that we actually have? Now, it's not really easy to just say this is what it means. I will try and give you an illustration of what we actually mean by this particular thing here. Let's start by saying these things in words and see what do we mean by this writing this whole thing. Remember that this is supposed to be here. So this one here is saying that the limiting, we have the limiting value of f, I can say f of x, or f is L as x approaches infinity. So the limiting value of f is L as x approaches infinity. Or we can say that the limiting value of f of x is L as x increases unboundedly. So our x is increasing unboundedly. That's the meaning of this whole thing, that this function is actually approaching this value as we keep increasing x unboundedly. Or as x gets bigger and bigger, this function is actually approaching that particular value. And if you look into this one here, is simply saying that, let me take a red there, this one is simply saying the following. The limiting excuse me, the limiting value of f, or f of x, is m as x decreases. So our x now is decreasing unboundedly. X is increasing unboundedly. So this one here is just saying that if, let's say, this was positive, we would say that f of x does not have, f of x is increasing. Suppose this one was positive, we would say f of x is increasing unboundedly as x increases unboundedly. That will be the meaning of that. Or if this one was negative, we would say that f of x is increasing unboundedly. I mean, it's decreasing unboundedly because this is negative. So as we're getting to the negative, the most negative numbers down there, we're actually decreasing this function. So as f of x is actually decreasing unboundedly as x increases unboundedly. And this one here, if we have a positive, would say f is actually increasing unbounded as x is actually decreasing unboundedly. You get what I mean? So most importantly, most people, or if this one is a negative, let's say this is a negative, not a positive, we usually say f of x is actually decreasing unboundedly as x decreases unboundedly. Some people usually say that to a different way to say. I'm actually saying the same thing throughout, but I want you to get used to these different phrases. Is this: the function f of x is converging to some value L as x increases unboundedly. So as we keep increasing x, because this is positive, so we keep increasing it, f of x is actually converging to that particular value. But in this particular case here, let's say this was positive infinity. This would say that f of x is increasing, f of x is diverging. So someone might come up with that and say it's actually not converging to some value because this is getting bigger and bigger. So f of x is actually diverging as x approaches or as x increases unboundedly. Or someone might just say actually f is actually approaching positive infinity as x approaches a positive infinity. This is also another way to say the same thing, right? Let's say now we have an example here. This is actually my plot, and my plot is going like this here, and this side here I have a nice plot. It is going like this, and then it goes all the way. Suppose this one here is a 5, and then it goes all the way like this. It does not touch this, but it keeps getting closer and closer to this particular value here. Now, and the question is like this: if I were to take a limit as x approaches positive infinity, what will be the value of that limit, or what is the limiting value of that particular function? And if I were to take the limit as x approaches negative infinity, what will be the value of that function, or what is the value or the limiting value of that particular function? So this is a 0 here. So as I'm going this side here, I am actually increasing. So this side x is increasing. As I'm going that side, x is actually decreasing, right? So as x increases unboundedly, so as x increases, what is this function actually doing? So you can see that this function was increasing just fine, but now as x keeps going further to millions and millions and trillions, what is the value of that function? You can see this function keeps approaching that value, but it's not gonna touch it. But if we keep increasing x, it's gonna get closer and closer. That if I were to plot this curve with a computer, it's going to say that it's gonna end up touching that point at infinity. So basically here, as we keep increasing this x, this function keeps getting closer and closer to 5. So this one here is actually the limiting value of this particular function f. But if we keep decreasing our x here, you can see that every single time I pick my x here, the output is there. And if I pick a different x somewhere there, I have an output there which is bigger than the previous output. And if I'm picking another x here which is most negative, the output is there, and that output is bigger than the previous output. As I keep picking this, the output is above the previous output, which means it's there. So as this x keeps decreasing, the y values or the output of this function is actually getting bigger and bigger, and it's not bounded at all, which means that as I keep going all the way to negative infinity, this function will keep increasing all the way up to positive infinity. So this particular function actually is going to be positive infinity if I'm actually going to the negative side of things. And I can take another example here and say that suppose now I have another function, and my function is f of x is equal to 1 over x. And if you look into this, we know this function that it looks like this. It nicely looks like this, and this side here it looks nicely like this. So as we are getting this function here, we can clearly see that now we actually have the limit as x approaches positive infinity of f of x to be equal to something. So I have a 0 here. The function is increasing as I keep increasing x, or as I'm increasing x. I can see that the function is actually getting closer and closer to this x-axis here. I have y there. So as I keep increasing, because this is increasing, this function is getting closer and closer to the x-axis. So if I were to continue this, it was going to get closer and closer and closer as we keep going this way. So the value that we keep approaching here, we're not going to touch it, but if we keep increasing x enough, this function actually is going to get closer and closer to y is equal to 0, or touch the x-axis. So this one is actually getting closer and closer to 0. And if we looked at the limit as x approaches negative infinity of f of x, in other words, negative means that we are decreasing the x-axis. So as I keep taking my x this side here, if I had an output there, I increase the output. You can see that is little above there, and it keeps increasing as I keep getting closer this side, or I'm getting moving to the to a negative infinity there. The function keeps going closer and closer and closer, and if I were to continue to draw this nice function here, it was going to get closer and closer and closer, but it's not going to touch this axis. But that value that we keep getting closer and closer to is just a 0. So that's the meaning of these two this limit here. That's how we actually found this limit. Those are nice examples, but what we actually trying to do here is this. If the limit, right, if the limit as x approaches positive infinity of f of x is equal to L, where this L is a finite value, right, we say that if f is equal to this, where L is a finite value, we say that that f of x has a horizontal asymptote at x. We have a vertical asymptote at y is equal to L. Remember that this value here belongs to the output, so it is our y, not the x. So let's look back to these two functions. You can see that this function is not going to touch this. So as x keeps increasing, this particular value becomes a horizontal asymptote, and the same thing this side actually happens. And if you also look into this example here, looking into this x f of x, as it keeps getting closer and closer to 5, it's not going to touch it. In other words, this x is equal to 5 act as a horizontal asymptote for this particular function. Yes, I know that the vertical and the horizontal asymptote, we are not supposed to touch it. That was the initial definition that you came across when you were still in high school. But now I want you to understand that when it comes to this particular portion of this function, we are actually getting closer to this, but we are not touching it. So this function is not going to touch here. So at x is equal to 5, we still have a horizontal asymptote for this function. Yes, I know that it touched here, but it's still a horizontal asymptote for this function because it's not going to touch there. So as x approaches infinity, this function is converging to this particular value. That's what is important by this. So these limits, what are they there for us to do? This limit as x approaches positive infinity or negative infinity. So if I have this positive or negative infinity, I get L, we have a horizontal asymptote at y is equal to L. So because we are trying to analyze a function here, what is important is that this limit, as we keep increasing x, we want to actually find out about are there any asymptotes that were horizontal asymptotes that we are getting as the function keeps going to positive infinity and also to negative infinity. So that is why we need this to completely analyze our functions. Hopefully you still understand what we're actually doing here, because in order for us to deal with this whole thing, I want you to get to understand the concept, or what we actually what is the meaning of this, that we're increasing x as x approaches infinity, and then we're actually decreasing x as x approaches negative infinity, and see what we're actually getting there. But here our x was approaching a finite value, but now this function is the one that was increasing unboundedly or decreasing unboundedly as we are actually approaching this particular value. So now we're switching things around now and say that our x is actually increasing unboundedly or is decreasing unboundedly, and want to say if is this function also increasing unboundedly, or is it actually decreasing is it actually decreasing decreasing unboundedly. So that's what is actually important. Now the question is, how do we solve in general? Because we don't want to get stuck with this idea of thinking that we can actually plot these functions. At this stage, we can't plot all the functions, but we want to get all the information that we can get out of the function. Even if you noticed, when we're still doing intermediate value theorem, I ran away from the idea of thinking that I can plot it, and I just wanted to analyze what was actually happening in between the 2 points. Now the question is how to solve limits at infinity. I'm gonna give you a couple of methods on how to solve this, and also another thing that I want you not to be trapped with when solving limits at infinity is this one particular thing, is that infinity is not a number, it's a concept of a big number. So I don't want you to say that infinity is no. Infinity is just a concept of a big number. We are increasing this x unboundedly to some big number that is up there. So this infinity is not like there is this number infinity. It is a concept of the big number that we cannot actually touch. That's the meaning of this infinity thing here. Now, to actually solve these limits, we first need to understand two things, right? In determinate form, forms versus determinate forms. Right. So I'm gonna just try and place a line here and go all the way down, and then we can actually talk about these indeterminate forms. Others, they like to say is determinate form or indeterminate form versus determinate form. Others are just saying is the algebra of infinity and zero. I am going to give you a summary of all these things that are important, and then once you grasp those things, you have to know them by head, and once you know them by head, it's gonna be easy for you to actually be able to deal with limits at infinity. Now, we talked about this and we said that if I have 0 over 0, this one here is always undefined. So because this one is undefined, we said that it is a indeterminate form. But don't mistake this with 0 times 0, because 0 times 0, we know that it is a determinate form and it is a 0. And if we take a positive infinity, and we divide this by positive infinity, don't mistake this and say, oh, this is just a big number divided by another big number, therefore it's supposed to be a 1. That's not actually the case, because this one also is undefined. We say it is undefined. But if you look into this, when I'm taking a very big number and then I multiply this big number by another big number, I'm supposed to get a very bigger number. Let me talk about this, why this is actually not the case. If I were to take 2 times infinity, infinity, we say that it is the very biggest number there is. So once I take a constant and I multiply a very big number, I would be able to get another big number. That's what is important. I will get back to this in a moment. Now, let me just list these two. This one, if I take a constant c, right, I'm just gonna write here that c is a constant that is greater than 0, is positive. If I take a constant c, I multiply this constant by infinity. So this constant times a very big number, I'm still gonna get another big number, right? And if I take this, I'm just listing it for a moment. If now I were to take again a 5, and I multiply this 5 by infinity, I get 5 and I multiply by a very big number. You can see that here I will get another big number, infinity, and if I multiply this by that, I will get another big number. But if you take note of this, I am taking this biggest number there is and I multiply by 2, I get that big number. I take this big number, which is that big number, and I multiply by 5, I still get another big number. So if I were to look into this number in a perspective that, suppose this was a number, some number, big number, and I multiply by 2, yes, I get a very biggest number that I cannot touch, but still this biggest number is not the same as that one, because I multiplied by 5 here, even though these two are infinity, but they are not the same. In other words, there are those infinity that are bigger than others and those that are smaller than others. That is why we cannot really say that this infinity is the same as that, or this one is less than this infinity, or this one is actually less than this infinity. We don't know what is happening, whether this infinity is bigger or this infinity is actually less, or the vice versa. That is why this one is actually not actually defined. And then what is the next thing there is here is that if I were to take, remember that I was dividing by positive and positive, right? So this one is undefined. So if I am taking a negative infinity and I'm dividing by a negative infinity, this is still undefined. And if I am taking positive infinity divided by negative infinity, or negative infinity divided by positive infinity, this is also undefined. But take a note into this, that if I were to take a negative infinity, I'm gonna clean this up. I will rewrite it at a later stage because I still want to compare here. If I take negative infinity and I multiply by negative infinity, these two big numbers that are big negative and negative is going to be positive, so I will end up getting the very big number infinity. And if, let's say, I'm taking positive infinity and I'm multiplying it by negative infinity, or I'm taking negative infinity and I'm multiplying by a positive infinity, I will get negative infinity. That's what I want you to actually get. And now if I were to take negative infinity and I subtract another infinity. Just like we said here that I don't know how big this infinity relative to this infinity. That is why we don't know what will be the answer, or is not defined yet. This is the same scenario here, because if I were to multiply one infinity by 10 and the other infinity by 100, I don't know which of these infinity is bigger. That is why we usually say that this one is also undefined, right? But take note of this. If I were to say I wanted to take positive infinity and I am plusing another positive infinity, I am taking two big numbers and I'm adding those two big numbers, I am supposed to get a very big number, which is still infinity. And when I'm subtracting a negative, a big number, I have a negative big number, and I'm subtracting from it another big number. This is actually the same as the negative big number. So these one are defined, and these one are really not defined. And if I were to take 0 and I multiply this 0 by infinity, right, this one also is undefined, right? It is undefined. But I don't want to make a mistake of saying that. I remember that here I'm multiplying. If I am taking a 0 and I'm dividing this by infinity, I have nothing, and I'm dividing by something that is so big, I'm still gonna get a nothing. So don't mistake that, because it's very important to be consistent and know these rules here. And if I am taking infinity and I am raising it to 0, this one is also undefined, or it is also another indeterminate form, undefined. And if I am taking 0 raised to positive infinity, that one we always say that is always going to be a 0. And now let us proceed. If let's say we are taking negative infinity and we are raising to 0, this one is undefined. But if I am taking 0 and I raise it to minus infinity, this one we know that it is an infinity, right? And if we are taking 1 raised to infinity, this one we say it is undefined. On this side here, if I'm taking 1 times infinity, we know that it is infinity. Taking 1 multiplied by a big number, it is infinity. And if I have 0 raised to 0, of course this one is also undefined. And this side here, I have some nice more things. So if I take a big number and then I take the exponent infinite number of times, this is still going to give us a very big number. And if I take a constant, whether the constant is positive or negative, and that constant I add infinity from it, I will get the biggest number. Whether this can be a million, as long as it is finite, this one will always overpower it, and we will always get a positive infinity. And if I take a constant and I subtract infinity from it, whether it's positive or negative, as long as this constant is finite, I'm always gonna get negative infinity. And if I take a constant and I multiply infinite with it, if this constant is positive, then I will get positive infinity if constant is greater than 0. This 1 times infinity, if this constant is negative, I will get negative infinity. That's what is important here. Like if they say this one is 2, then 2 times infinity is going to be infinity. If this one is minus 2, 2 times this infinity is going to be that thing here. And then lastly, whenever I have a finite value, whether this is positive or negative, and I divide that value by infinity, this one is always going to be 0. That's what is actually important. I understand that once I divide this as determinate form or defined values versus indeterminate form, so I want you to know these things by heart because you need to know them when you are actually dealing with the limit at infinity. When we are saying 1 raised to infinity is undefined, most students are actually getting alarmed because they think that is 1 times 1 times 1 times 1 times 1. Whenever I'm multiplying 1 by itself, I'm still gonna get a 1. But the main reason behind why this one is also undefined is because once I can say that this one is equal to 1, let us see what is actually going to happen here. I'm going to suppose that 1 raised to infinity is equal to 1, as most students usually claim. Like I said, this one here is undefined. It's not. This is not the case. This one is undefined. But now, suppose that you are arguing that actually this is supposed to be equal to a 1, which is not true. Which is not true. Let me cancel it here. Is equal to 1. Let's assume that this is happening. If this one is happening, we will end up having 1 raised to infinity is equal to 1, which means that if I were to take a ln on the left, 1 raised to infinity, and get a ln on the right, I know that on the right I would end up getting a 0 because ln of 1, the natural log of 1 is 0. And now, whenever I have a log function that has an exponent, I can always bring the exponent down. So I have infinity times ln of 1. And now, if you look into this, we know that ln of 1 is just a 0. So infinity times 0 is just equal to 0. So you will end up having something like this. What this thing is actually saying is actually saying that you were lying when you actually said that 0 times infinity is undefined. 0 times infinity is actually defined and it is equal to 0. If you are saying that this one is supposed to be true. And if you look into this whole thing here, this simply means that if, let's say, I have this, you know that whenever I have a constant divided by infinity, this is equal to 0, or 0 is equal to 1 over infinity. This simply means that this we will end up having, instead of 0, I will say 1 over infinity is equal to 0, which is this 0. And infinity times 1 is going to be infinity over infinity is equal to 0. Which also means something else, that actually when you were saying that infinity over infinity is undefined here, you were lying. This one was supposed to be a 0. So by assuming that this one is defined to be equal to 1, you are actually defining these whole things here. But let's continue and see what is going to happen here. Remember that here there is a 1. If I were to cross multiply here, I would end up having infinity is equal to 0 times infinity. And now, if you look into this whole thing here, you find out actually that infinity, 0 times infinity. So we first found out that 0 times infinity is equal to 0, which was actually here. 0 times infinity is equal to 0. And now we are also finding out now 0 times infinity is equal to infinity. And infinity and 0 is not the same, which is a contradiction. So the reason we are saying that this one here is undefined, because once you define it to be 1, you actually are going to contradiction. You are reaching contradiction. Even if you were try to define this to be equal to 1, you would actually end up finding some contradictions. So this one here is actually not true at all. So don't even try and say this one is going to be true. And as nice as you might think it is that you want to make it true, there are several things that I would say. I would say that continue and do your master's and your PhD and do one of these and say that actually you have defined it, you might have a paper. Think about it. And if it happens that your paper is going to be accepted, then I would say that actually you are actually a genius that actually redefined these things and said that actually we can define them and still not reach certain contradictions. Or you can define them and justify your contradiction. That will be depend. For now that you still haven't touched your masters yet and you haven't started with a PhD or in your way to actually redefining this and convince the whole world that these indeterminate form are actually need to be determinate form, you still need to accept what I'm telling you, which is 0 over 0 is undefined, infinite over infinite undefined, negative infinite over infinite undefined, negative or positive infinite over infinity undefined, infinite minus infinite is undefined, 0 times infinite undefined, infinity raised to 0 undefined, negative infinite over 0 undefined, 1 to the power, all these things undefined, and those that are defined are on this particular side here. You need to know these things one by one. Now that we have actually dealt with these whole things now, you know them. The question is how to solve. Okay. We have now how to solve the limit as x approaches positive or negative infinity of f of x. How do you solve this particular function? Right. I have 3 things that I can tell you that you can try. Specifically, there are 2. There are only 2, but I expand them to 3 so that if someone is saying that there are only 2, don't say that they are wrong. I just decided that to expand them to 3, I mean. And even if someone is saying that there are more than 3, they decided to expand even further, but I'm going to give you these 3. The first one is this. If when we are taking we suppose that we can touch this value infinity here and we can plug it inside there and we are actually getting a value, then that is actually the limit that we're looking for. Let me try and see and write it. If we evaluate, right, the function f at x is equal to positive or negative infinity, and we get a determinate form, right? We just evaluate the limit, right? This is because we will be able to evaluate the limit with no issues. Just by applying some algebra. So the first one is, if let's say, I know this one can make different mathematicians to have different arguments, and they would have reasonable arguments. Let me explain what I am trying to do here. Maybe it's going to help you to understand this whole thing. Since we said that infinity is a concept, it's not actually a number, then we cannot say we're gonna take infinity and plug it in a function. But now, because I want you to actually relate to what we're actually doing, that whenever we have a value here, we first plug it in here and see what we are actually getting. So I am using that philosophy there, that assume that we can grab this little infinite, and then even though we cannot touch it, suppose that we were in a case whereby we can grab it in and we can plug it in there. And if it is possible for us, when we are plugging it in there, we are getting something that is on this side here, determinate 4. Then what we actually do, we can just evaluate that limit just like that, and apply some algebra, the algebra on this side, or manipulating whatever we're getting to fit something that is in this side, so that we can actually evaluate that particular limit. Let me take an example here. Maybe this is going to make some sense. Suppose we are saying that evaluate the limit as x approaches negative infinity of e to the power x. So we know that we cannot get touch negative infinity, but we're gonna assume that we were able to touch this negative infinity, right? Now, if you look into this, there is something that is missing here that I did not add. I think it's the last one here. If I have a constant, right, this constant c is bigger than 0, and I raise it to infinity, I take a constant and I keep multiplying by itself infinite number of times, I am going to get infinity. So this is always going to be the biggest number there is. So if I get 2 times 2 times 2 times 2, that number keeps getting bigger and bigger and bigger, and then I'm going to end up having some infinity. Now, let's look into this one here. If, let's say, I am getting this thing here, I said suppose that we were able. Remember that this infinity is not saying that there is a number here. This is saying that x is decreasing unboundedly. It's not saying that there is a number, negative infinity. No, negative infinity is a concept. But now, I'm saying suppose you were able to take this as a number and you were to plug it in there. Is it allowed? Most people are saying it's not allowed. I'm not disagreeing with them, but now for the sake of solving limits, I'm saying suppose it was. So if it was, we were going to end up having e raised to negative infinity. And whenever you have a negative exponent, you know that you end up having 1 over e raised to a positive exponent. Negative exponent means that we have 1 over. Right. And if you look into this, I have a constant. E is equal to 2.7 something. So it's bigger than 1. It's not 1. So when you are raising this to this exponent infinity, it's a constant raised to infinity, positive in constant raised to infinity. It's actually going to be 1 divided by, this is getting bigger and bigger, so it's going to be infinity. Now let us look into this. Let me finish this, and then I will explain the more allowed way to do this. But this one makes things easy because you're just using one of the determinate form, because 1 is a constant divided by infinity. I know that whenever I have a constant divided by infinity, I am always going to end up getting a 0, because I have 1 divided by the very biggest number. So even if I were to say I have 1 divided by 10 raised to, let me say I'm gonna end up saying 80, the biggest number there is. If I okay, let me say now I have as many zeros as I can here, because we cannot touch infinity. You can see that this calculator is just saying you are actually having an error there, and if I reduce, you still have an error there, and when I reduce, I still have an error there. When I reduce, I still have an error there. When I reduce, I still have an error. When I reduce now to 80, I have this whole thing here. And if you look into this, this is saying that you have 0,0000000000000, and you have 80 zeros, and then you have a 1. No, you have 79 zeros, and then you have a 1. So this is actually, you can round off, because when you're rounding it off, you will end up having a 0. So this is like this. If someone is fair and they understand that you are actually assuming you were able to plug in, you're supposed to have full marks here. Someone who is actually more strict on this, they don't want you to do this. They want you to understand this whole function here and understand that if you are dealing with an exponential function of this kind here, this exponential function looks like this, because this one is y is equal to e of x, and e is bigger than 1, so this is increasing like this. But now, having this part here is actually saying that we have a 0 here. We are decreasing to this side. So as you are decreasing this to negative infinity, what is the value this function is actually approaching? So as this function, if I were to continue to draw it, it was going to go all the way like this, and it's getting closer and closer to y is equal to 0. Hence the limit is going to be equal to 0. So if it is possible for you to draw this function, you can draw this function, and from this you can deduce that the limit as x approaches negative infinity of e to the power x is 0. So you can either have this function, get your 2 marks, and then get your 1 mark for analyzing what is happening, or you can actually decide that no, I'm going to assume that I can plug in. Because I can plug in, I will say that, when I'm plugging in, I will have that negative, and then when I have that negative, it means 1 over, and a constant raised to infinity. As long as that constant is infinity, is always that constant is positive, we're always going to have infinity. You get another a particular answer. By knowing that when you have a constant divided by infinity, you get a 0, you can still get the same thing. So it's up to you if you want to go this way or that way. And of course, like I said, some people don't like this idea of saying we're plugging in infinity, because infinity is actually a concept of a big number. It's not really saying we have a big number there. Let's take another example here. This example is saying that evaluate the limit as x approaches positive infinity of cosine of 1 over x. So I have cos 1 over x, or evaluate the limit as x approaches negative infinity of sine of 1 over x. So if you look into this, if we were allowed to plug in here, this was supposed to be cosine of, take note of this, a cosine function is continuous everywhere because you can just draw it without lifting your hand, so it is continuous everywhere. So I can always say that I'm going to take this and try and put this inside. So if this is plugged in there, I'll end up having 1 over infinity. And 1 over infinity, a constant over infinity, is just the same as cosine of, once you divide this, the answer you're going to get is just going to be 0, because this is way too big. So the answer that you'll end up getting is just a 0. And we know that cosine of 0 is just a 1. So this limit here is actually going to 1. I don't want you to confuse this with x approaches 0, because that's actually a different understanding of what might end up happening here, because we don't know what becomes inside when we are getting closer and closer to 0 of 1 over. We don't know. That's why it becomes undefined. But for infinity, I know that when I take 1 divided by infinity, I'm going to get a 0, and cosine of 0 is 1. And if you look into this, I will end up having sine of 1 minus 1. Remember that I have this is 1 over negative infinity. And if you look into this, I will end up having sine of this is the same as negative 1 over infinity. So you can see that negative 1 is still a constant. A constant divided by infinity is always going to be a 0. So you have sine of 0, and this is a 0. So these are other methods of actually trying to solve this limit. So that was number 1, whereby whenever you are plugging in here, you are actually getting a determinate form and a value that actually can be solved. So in that regard, we can continue and say that we can solve. Now, I want us to go to the second one. The second one is not difficult, right? So this one is just saying that if we evaluate, right, the function f, right, at some x equal to plus or minus infinity, right, and we end up getting indeterminate form. We do the following. Okay. These indeterminate forms are different, right? Once you get a 0 over 0, you are actually fine. Once you get infinite over infinity, you are also fine. Once you get infinite over infinity, you are also fine. Once you get infinite over infinity, you are also fine. And all these other things are actually happening here. So this is what I'm going to suggest here. Let's go back to what we're doing here. If, let's say, I'm going to take the first case here. I'm going to say A. If, let's say, I want us to get a 0 over 0 or infinite over infinity, something of that nature, and then we'll be able to actually deal with this whole thing. In a nutshell, let me give you a summary of what I'm going to do, because that's what is important here, just in case we don't get enough time to continue forward. Whenever you are getting something of this nature, any of these things that are inside like this on the indeterminate form, your main goal is to convert these things to actually become determinate form. Let me repeat what I'm saying. Your main goal, once you end up having this particular thing here, you want to make sure that you convert an indeterminate form to determinate form. So let me write this first. I'm gonna write this. Your main goal here is convert in determinate form to determinate form. So that's the main goal that you want to do. You want to convert indeterminate form to determinate form. So the first way to do this is, if f is a rational function, take note that a rational function is when you have a polynomial over a polynomial. So if we have that, what we do here, we take the highest power in the denominator. So we factorize both the numerator and denominator, but this factorization is unique that we just want to factor out the highest power of the denominator in both the numerator and the denominator. So we take the highest power in the denominator and divide This is not divide. Divide, this is supposed to be I. Divide both the numerator and denominator. We divide both the numerator and the denominator. Then once we do that, we'll be able to evaluate the limit. We'll be able to evaluate the limit. Let's take some examples. This is actually going to be so easy when we are taking examples. Let's take one or two. Suppose the question is saying, this is the first example, evaluate the limit as x approaches infinity of 2x squared minus 3x plus 7 all over x squared plus 47x plus 1. Right. Now, if you can notice here, there is something that you can notice here, is that if I were to plug in infinity here, infinite squared is going to be infinite times infinite, and infinite times infinite is infinite. Taking infinite and then multiplying by 2, I will get infinity. But now, once I subtract 3 times infinite, I will get infinity minus infinity, which is a problem. And then if I deal with the denominator is going to be infinity plus 1, which is infinity. So I'll have a problem in the numerator with this infinity. In other words, I will end up getting indeterminate form. So what this thing is saying, go to the denominator. In the denominator, you can see that actually, look for the highest power. You can see here the power is 2, the power here is 1, and the power here, we have x raised to 0. So the highest power is going to be this x squared here. So to find this limit, we just say that this limit has to be the same as x approaches infinity of, I am going to factor out x squared in the numerator. So I'm going to factor x squared in the numerator. So if I'm taking out x squared, I will end up being left with 2 minus 3 divided by x, because 1x is gone here, and then we need one more x to actually take out, so we end up having this. So if I can say 3x divided by x squared is going to be x divided by x, and then plus 7 divided by x squared. You go to the denominator and we do the same thing. I'm gonna have x squared, and then in the denominator, x squared divided by x squared, I will end up having 1, and then plus, and then I will have 47x divided by x squared. This x here will be gone, and now you'll be left with 1x in the denominator, and then plus 1 divided by x squared. That's simple as it is. And then secondly, this x squared and this x squared will cancel out, so now we are left with the limit as x approaches infinity of 2 plus 3 divided by x plus 7 over x squared all over 1 plus 47 over x plus 1 over x squared. So if you look carefully into this particular thing here, you will find out actually that if I were to plug in here, I was allowed, remember that infinity is not a number, it's a concept. Suppose now we are treating this infinity as a number and we plug it in there. We'd end up having 2 plus 3 divided by infinity plus 7 divided by infinity squared, or infinity times infinity, and then all divided by 1 plus 47 divided by infinity plus 1 over infinity times infinity, or infinite squared. Now if you look into this, we said that if I take 3 and divide by the very big number, this 3 will be insignificant and you will end up having a 0, because 3 divided by million, you will end up having a 0, plus taking 7. Okay, infinity, a big number times a very big number, is going to be the big number, like we said with the determinate form. And then when you're dividing the biggest number, dividing 7 by biggest number, you're always gonna get a 0. And then the same is going to happen here, because 47 is insignificant compared to infinity. So once I'm dividing this by infinity, I'm always gonna get a number that is close to 0. So I can just round it off to 0. And then here the same thing is going to happen. 1 divided by infinity is going to be a 0. So this limit evaluates to 2. You see how easy this thing is. Let's take another example here. The second example is saying evaluate the limit as x approaches infinity of 2x squared plus 3 all over 5x squared plus x. Now, the first thing that you need to do here is that I want the highest power in the denominator, and this one is 1, this one is 2, so the highest power is x squared. So I'm still gonna have the limit as x approaches infinity, and then I'm gonna factor out the highest power. So I will have x squared, not x subscript to x squared in the numerator, and then I'm gonna have 2x squared divided by x squared, because I want to factor out that, plus 3 divided by x squared. And then in the denominator I will end up having the same x squared, and then I will end up having 5x squared divided by x squared plus x divided by x squared. And if you notice, this will be the same as the limit as x approaches infinity. This and that will cancel out, and now x squared divided by x squared is going to be just 2. 3 divided by x squared is going to be 3 divided by x squared, and then x squared divided by x squared is 5x squared divided by x squared is going to be just 5. And then here I will end up having 1 over x. And if you proceed here and you are allowed to plug in, you will end up having 1 plus 3 over infinity squared, which is the same as infinity times infinity. And infinity times infinity is just infinity. And then divide by 5 plus 1 over infinity. Take note that this one was infinite squared, which is the same as infinite times infinity, and this is a determinant form, and it was equal to infinity. Now 3 over infinity, we know that any constant divided by infinity is 0, so we end up having 2 plus 0 divided by 5 plus a constant divided by infinity is just 0, so this limit is 2 over 5. That's also very easy. These things are not really that hard. So now what we actually do now, because we had a rational function, so if we have a rational function, we just factor out the highest common, the highest power of the denominator in both the numerator and denominator, and then we cancel it out, and then what we will end up getting, it will be a determinate form. Now the second one, 2, if f is not a rational function, is not a rational function, then transform indeterminate form to determinate form. That's what we actually do. How do you end up doing this whole thing? You can do this one by factorizing. You can either factorize factorizing f, or by bringing the exponent down. So if you end up you were having 0 raised to 0 infinite raised to 0 or something of that nature, how do you end up bringing the exponent down? We use log functions. We use log functions and e. So we use log function and the Euler number e. That's what we actually do. Bring down the exponent, or what we do, create a power. So you can either create a power. In one words, let me just put this like this. In one words, I would say that what you can actually do here, we can just say simply use algebra to manipulate. So we are just manipulating the function f and see if we can actually get what we're actually looking for here. Let me take some examples here. I have a. So suppose I want us to evaluate the limit as x approaches positive infinity of x cubed minus x. If you take note of this, if I were to plug in this here, I would end up getting infinity cube minus infinity. This is the same as infinity times infinity times infinity minus infinity. And if you note into this infinity times infinity is infinity. Infinity times infinity is infinity. So I'll end up having infinity minus infinity. Because I don't know if this infinity is bigger than that infinity, or this infinity is bigger than that infinity. I don't know, or they are equal. So this one is an indeterminate form. So how do I remove this indeterminate form? I can do it by factorizing this whole thing. And if you note now, we'll end up having x approaches infinity. X is common in this term and that term. I'm going to end up having x, and then I'll be left with x squared minus a 1. And if you take a note into this, now that I have this, I would end up having infinity and then infinity squared minus 1. And if you look into this, I will end up having infinity, and this is infinity times infinity minus 1. And if you look into this, this one here will end up having infinity times this infinity times infinity. We know that it is actually infinity, and then infinity minus 1. Of course, 1 is so small compared to infinity, so we end up having infinity minus 1 is the same as infinity. So infinity times infinity is just going to be infinity. So this limit is actually evaluating to itself to be infinite, or we can say that this function is actually diverging as x increases to positive infinity. So that's what is actually happening here. So we can either actually factorize and see what we are actually getting in this particular case. So we just manipulate this whole thing and see what we are actually getting. So that was the second method of solving this. The last method is saying this whole thing. If when evaluating f at x equal to either plus or minus infinity, we are getting zero over 0, or we are actually getting infinity over infinity, right? So if we are getting this or that, use L'Hopital's rule. We haven't done this, but I want you to know that we can use L'Hopital's rule. What this thing is simply saying is this: if it happens that when you're trying to evaluate this limit here, suppose you're trying to evaluate this limit as x approaches infinity of f of x, you are actually, if I take this and I plug it in there, maybe I'm getting 0 times infinity. If you take a note into this actually is going to be the same as 1 over infinity times infinity. So we end up having infinity over infinity. So in this case here, once you end up having this, you have to manipulate your function so that you end up having infinity over infinity, so that you can use L'Hopital's rule. That's what this is important. Manipulate your indeterminate form so that we end up having this thing here, so that we can use L'Hopital's rules. So there are 3 methods to do this. You factorize. If you can plot, the first one was just, if it's possible for you to plug in, you can just plug in and see what you're getting. If you are not plugging in, you must be having a rational function. If you're having a rational function, look at the highest power of the denominator, factor it out, and then simplify. If that is not the case, cannot be done, then manipulate the function so that it becomes a determinate form. You can do that by factorizing or bringing down the power or recreating the power. If that cannot also not be done, then you can actually manipulate this to fit this or that and use L'Hopital's rule. Let us take some examples, and then after those examples we can actually call it a day. So I'm gonna say these are the examples or exercises. These examples are saying this one thing: evaluate the following limits. So the first limit here is saying that you have the limit as x approaches infinity of e to the power minus x times cosine of x. I'm gonna give it some space so that we can rewrite, and then the second one is going to be here. We will have the limit as x approaches infinity of x squared minus 2x plus 3 all over, I have x cube plus 1, and then I'm gonna leave some space and try here and say we have the limit as x approaches infinity of 6 divided by the cube root of, the square root of x cube here. And then the fourth one, I want us to find the limit as x approaches infinity of x cube plus x. And then the last one here is going to be e. I want the limit as x approaches infinity of x squared minus x. Right. Let us do this one by one. So if you look into this, of course, we said the first thing that we need to try and do here is to simplify and see what we can actually get before doing anything. So this is the same as cosine of x, and then in the denominator here, I have e to the power x. The negative exponent is just meaning that we have e to the power x in the denominator. And then the next thing that you have to realize here is this. I want us to plug in this infinity and see what we're getting. So if I'm looking at cosine of infinity and I have to divide this by e raised to infinity, this is what we will end up getting. A constant that is positive raised to infinity is the same as infinity. But cosine of infinity, we don't know the value at infinity. The value can be positive 1, it can be negative 1, it can be a value that is in between negative 1 or positive 1. So I'm gonna call that value some m. I don't know what that value is. So because that value, I know that it is a value that is between -1 and 1. Taking that value and dividing by infinity, that value is going to be so small compared to infinity. That is why this is just going to be a 0, because a constant divided by infinity is just a 0. Let me repeat what I'm saying. I don't know what is happening at infinity. If I were to say the limit as x approaches infinity of cosine of x, this one here, I would say that it does not exist. Why? Because I don't know what is happening at infinity, because it can happen that at x is equal to infinity, this value here can either be -1, or it can be +1, or it can be anything. So I don't know what the value is, so we would say it does not exist. But now we have something in the denominator, because in the denominator here, okay, let me just complete this. This would end up having cosine of infinity, which we know that it does not exist because we don't know that value. But now I know whatever that value would be, it would be between 1 and -1. But now dividing whatever that value by infinity, that value is going to be so insignificant compared to infinity. Hence, dividing by infinity is just going to give us 0, because infinity is so big compared to whatever that value is. That is why we end up having a 0 there. So don't confuse the two things here. It's because here the reason it exists is because here and there I can always divide, I can always simplify the denominator, but here we don't have anything else. We are left with that. Let's look into this one here. You can see that this whole thing here is a polynomial and this one is a polynomial. So this whole function is actually a rational function. So the highest power in the denominator is x cube. So this is going to be the same as the limit as x approaches infinity. And then I'm going to factorize x cube in the numerator. And then what will remain is going to be x squared divided by x cube. Minus 2x divided by x cube plus 3 divided by x cube all over. I'm going to factor out x cube, and then I will have x cube divided by x cube plus 1 divided by x cube. And of course, this x cube and that x cube, they cancel out, and now you are left with the limit as x approaches infinity of x squared divided by x cube is just going to be 1 divided by x minus 2 divided by x squared plus 3 divided by x cube all over 1, because x cube divided by x cube is 1 plus 1 over x cube. Now, if I were to plug in infinity here, I will end up having 1 over infinity minus 2 divided by infinity squared, or infinity times infinity, and then plus 3 divided by infinity cube, or infinity times infinity, all over 1 plus 1 over infinity cube, or infinity times infinity. And if you look carefully into this, you will find out that 1 over infinity is just 0, minus infinity times infinity is infinity. Big number times a big number is the biggest number. So having infinity, 2 relative to infinity is just insignificant. So 2 divided by infinity is just going to be 0 plus, and 3 divided by this, infinity times infinity is infinity. Infinity times infinity is infinity. 3 divided by infinity is just going to be 0. So we end up having 0 all over 1 plus infinity times infinity is infinity, times infinity is infinity. 1 divided by infinity is a 0, so we have a 0. So this will be equal to 0. 0 minus 0 is 0, plus 0 is 0, divided by 1, which is just 0. So whenever the highest power in the denominator is bigger than the highest power of the denominator is more than the highest power of, is bigger than the highest power of the numerator, that limit is always going to end up being 0. But if this one is always bigger than the highest power of the denominator, that limit is there are higher chances that it's actually gonna go to positive infinity or negative infinity. But if the power of this is the same as the power of this one, then the limit of this will be the coefficients of these two powers. In other words, we'll just take the coefficient divided by the coefficient of that, just like we did in the previous example that we actually had. Now, this one here is the same as, I can just take this infinity and plug it in there. I will get 6 divided by the square root of infinite cube, which is the same as infinite times infinity. Right. If you look carefully into this, you'll find out that this is 6 divided by infinity times infinity times infinity is going to be the square root of infinity. And because infinity is the biggest number there is, so if taking the square root of that infinity is just the same as actually getting infinity. So 6 divided by infinity is just going to be a 0. Another way to look at why the square root of infinity is this. Is because we know that infinity times infinity is infinity, which means now when I'm taking this is infinity squared should be equal to infinity. When I'm taking the square root of this and the square root of that, I should get the same answer. The square root of this whole thing will actually give us infinity, and the square root of this will actually give us, because this one, the square root is always positive, so even here we should also get infinity. So that is why we're getting a 0 here. And this one here is simple, because all we just need to do here, factor out x. We still have the limit here as x approaches infinity. I factor out x, and then I will end up having x squared plus 1. And this whole thing is going to tell us that this is the same as infinity times infinity times infinity. Infinity squared is going to be infinity times infinity plus 1. So basically I have this infinity here times infinity is infinity plus 1. So adding a 1 is not going to change infinity. So we end up having infinity times infinity, which is just infinity. So that's the value of this limit here. The same thing here, we're going to end up having in limit, the limit as x approaches infinity of x, and then we end up having x minus 1. And this is going to be actually infinity times infinity minus 1, which is just infinity. The biggest number minus 1 is still infinity, which is just going to be infinity. So I would say let's stop there at the moment, and I will try and look for other examples now whereby you are actually needing to bring the exponent down, and then I will see if that video can actually be uploaded and see if you can actually grasp the content of what we are actually doing here. Technically, there are 3 things that are actually important for you. Is that if you can plug in, just plug in, because the main goal is to change indeterminate form to be determinate form. That's what is actually important here. Let's just stop there for now. Let's just stop there. You must be tired.